Hi everyone, another video just showing my efforts on the MAT 2022 this year. So this was the short questions F to J. Now, let's take a look at F. This if you're doing double maths, you better get used to these kinds of questions because it looks very similar to some of the questions which they've asked before, where you firstly establish a result with something called de Moivre's theorem, and once you've established that result, you can find exact values of sine and cos. So it's one of those ones where you've got an advantage if you've seen questions like this before, because it's pretty standard really. Now, what do I mean by that? Well, firstly, let's actually have a look at this. Can I firstly say let S equal sine theta? It will just make my working out slightly quicker. I can say therefore that sine 5 theta, yeah, is identical to, I normally use identical to because it's for all real theta, 5s minus 20s cubed plus 16s to the 5. We can, of course, factorise that, so sine 5 theta is identical to s times by 5 minus 20s squared plus 16s to the 4. And so let's have a look at what we've done here. And let's try and relate this to sine of 72, yeah? Clearly, the left-hand side is identical to the right-hand side, and it would be nice, though, if the right-hand side equaled 0. Well, guess what? When theta is 72, the left-hand side does equal 0, because 5 times 72 is 360. And so if we let theta equal, if we consider, let's put it like this, consider that the left-hand side is equal to 0 when theta is equal to 72 degrees, yeah? In other words, the left-hand side will be 0 when theta is equal to 72 degrees. So we can write 0 equals, if we just say theta is going to be 72, then we can say 0 equals s times by 5 minus 20s squared plus 16s to the 4, yeah? Now, remember, these should also give us values for sine theta, which is sine of 72, remember. But it doesn't just give us values for sine of theta, because, sine of 5 theta is 0 for tons of values, an infinite number of values. But this is a well-known trick for finding exact values for sine of 72, sine of 144, sine of 216, sine of 288, and if you like, sine of 0 or sine of 360, it depends basically. It will actually just repeat, because we know that sine, the sine and cosine curves repeat in a really nice pattern. But what this basically does, that first s is going to give you the value for sine 0, because when theta is 0, because remember s equals sine theta, so when theta is 0, sure enough, sine 5 theta is 0 as well. So that kind of corresponds to the root available here. But for the 4 roots you get for this quartic, that corresponds to sine of 72, sine of 144, sine of 216, and sine of 288. So let's consider the quartic. Yeah, and you're going to be doing this a lot next year, or these kinds of questions, they pop up all the time. 20s squared plus 16s to the 4 equals 0. And so probably wise to let u equal s squared here, just so we have a nice looking quadratic. Everybody prefers a quadratic, don't they? And then we can complete this. How did I finish this? I did it by completing the square, actually. So I divided everything by 16 first. So I've got u squared minus 20 over 16, which is minus 10 over 8 u, which is 5 over 4. I'll cancel that in a minute. Plus 5 over 16. So I've divided everything by 16. I'm now going to halve the middle term, which is handy actually. I'll just leave it as 5 over 8. And then I've got minus 25 over 64 plus times top and bottom by 4, 20 over 64 equals 0. And so u equals, let's just finish it off now, shall we? That's minus 5 over 64. Add it over, you're going to get 5 over 64. Then you're going to be square rooting that 5 over 64. And then you've got 5 over 8 at the start. And there's a plus or minus, and that 5 over 8 you're adding over. Okay, so remember u as well as s squared, so we can see that s equals the square root of 5 plus or minus root 5 over, and we can square it to 64, can't we? And we've got common denominator, and then we've got 8, and there's a plus or minus out here. So there's your 4 roots. 2 roots because of a plus or minus in there, but 2 more corresponding to each of those because of a plus or minus out here. And that's why all of these signs are that way around, if you see what I mean. What they've done is they've written down the 5 roots of the quintic equation when you've got the power of 5 up here. That's what they've actually done for this question. They've just said just write down the 5 roots. Now, the hardest bit of these questions in some ways is identifying which root is for you. Yeah, because these roots, you know, we know theta is 72, but theta could have been 144, 216, 288, and all other kinds of multiples of 5. But if we just look at the principal roots here, that would be handy because it's just going to repeat after that. Think of the sine theta graph. Remember, S is sine theta. The sine theta graph looks obviously like this. And now just think about roughly where they are. 72, bearing in mind that's 90, yeah? 72 is like here, yeah? And then 144, well, that's closer to 180, so that's lower, like there, yeah? And then we're going to get, after 144, what do we get? 216, which is 36 above 180 rather than being 36 below 180. And then we're going to get 288, which is close to 270, and it's like over there, yeah? Now, these are your 4 roots. This one corresponds to the one we want, which is plus root 5 over 8. This one corresponds to, because it's slightly lower, just by reasoning it's slightly lower, 5 minus, it's still positive low, isn't it? 5 minus root 5 over 8. This one corresponds to, and it's positive, minus of 5 minus root 5 over 8, and the bottom one is minus of root 5 plus root 5 over 8, and so that must be the exact value of 288, that must be the exact value of 216, I think it was, that must be the exact value of sine of 144, and this is the exact value of sine of 72. So the answer is A, I think. There we go. Okay, did I have that? Yeah, I did have A. Okay, G. Okay, so Arx had asked me about this one. Some good questions there as well. I'll be honest as well. I got this right, but not because I used their trick. I ended up doing some crazy stuff, actually. I'll show you what I did. It's really silly what I did, but I just wanted to know the answer. And sometimes you can kind of ignore their instructions. Sometimes you can't, but sometimes you can. They're asking what we can deduce about n to the 4 plus 4. Well, straight away I thought, well, if n is 1, you've got a prime number, so that rules out A. Yeah, it is sometimes a prime number, so this definitely doesn't show that it's never prime number, because sometimes it is a prime number. When n is 1, for example, it's a prime number. So we've got these possibilities, yeah? Now, I looked at this as well, and I didn't see the substitution. Yeah, they've got a very clever substitution. Now, you asked about substitution. I want to talk specifically about substitution with identity, because this is an identity, because it's true for all real n, yeah? So really, you know, we could put an extra line in there. We don't always do that in maths. It's not obligatory to write as an ident, you know, with the super equals, as I call it, but it makes it sometimes nicer in your working. I just wanted to point out, with an identity, you can do some cool stuff, because, for example, x plus 1 squared is identical to x squared plus 2x plus 1. Well, we can work out all kinds of other identities from an identity using a substitution. So, for example, I could say let x equal 3y, yeah? And then I will know what 3y plus 1 all squared is, because I'll just need to substitute 3y in there, I get 9y squared, substitute 3y in there, I get 6y, and then I get the 1 on the end, and that is the correct expansion of that. My point is, if you use a substitution here for something which is holds for all real n, yeah, well, if it holds for all values, it holds for when x is 3y. And so when you plug in 3y on both sides of the identity, you're going to find that the identity is true. You can even do other cool stuff with identities. I've often pointed this out to my class, that if you've got, for example, here's a trig identity, sine 2x is 2 sine x cos x. What happens when we differentiate an identity, both sides with respect to x? Well, we get another identity. Watch this. Sine 2x differentiates to 2 cos 2x. And that is indeed identical to, okay, I'm going to use product rule here for this. Differentiate sine. I'm going to leave the 2 parked outside, because constants just hang around in calculus, don't they? They don't really do much when you're timesing by a constant. Just leave it sitting around. Okay, differentiate the sine x, you get cos x, times it by this side undifferentiated, plus differentiate this side, sorry, you're going to get minus sine x times by that, you're going to get minus sine squared x. Oh, and look at this. We've got the double angle formulae now for cos after differentiating it. Isn't that nice? Because the two's would cancel, and that's double angle formulae for cos. So what I'm showing you here is that when you start with an identity, there's all sorts of things you can prove. More, tons and tons more identities you can prove from an identity. And that's because that is identical to that. So of course they should have exactly the same derivatives, yeah. And those derivatives, while they look different, it gives you another identity in it, yeah. So that was my first point. So when they say that this is true, what we can do is we can plug in anything as n here and come up with another identity which will also be true for all n or m or whatever it is letter that you're using. Now I will explain their way of doing it. Can I just point out my embarrassing way of doing it first? This is not a good way of doing it. I'm not trying to sell it to you, but I do like pointing out that when you do these questions in test conditions and stuff like that, firstly you're going to make some mistakes. You're going to get some stuff wrong. We're all only human. I had a look at the Tom Rocks video when he works through the step, and I love the fact that he did it properly in time conditions, because there's little snipey comments underneath saying, you wouldn't have got full marks for that, you would have only got 18 out of 20, and it's like, this is the point. People far cleverer than ourselves are doing these papers and still making the odd little mistake here and there. Don't feel bad if you make an odd little mistake here or there. It's normal. Okay, so this was my silly way of doing this. Okay, I just thought, I'm not sure. I think it's probably B, because I've got a 5, a prime number, what n is 1, I get 5, that's absolutely fine. And so what I'm going to do, I'm going to think about just n to the 4 plus 4. I'm going to think about if I can factorize it, yeah? So I thought, can I factorize this? Okay, factor theorem, that says, well, I need to find out if I can find a value which I can plug in for n and see if it equals 0. Now, what about 2i? Yeah, I didn't say this was a good method. I just said it was my method. Yeah, 2i, of course not, actually, because 2i is going to be 4i to the power of 4. That's not going to work, is it? So I thought, well, okay. Sorry, I've just been put off because some of my family have come in and started asking me stuff. Okay, so I've got n to the power of 4 is minus 4, so I then fourth rooted it, and so I want the square root of minus 4, sorry, the square root of minus 4, which is going to be square root minus 4 is 2i, so I want the square root of 2i. Yeah, and that is going to be root 2 times by the square root of I. Now, the square root of an I is an old question you might get asked in a university interview. Best way of handling it really is to realise that if you're at I and you want to square root it, well, because it's got a modulus of 1, and we just, so the modulus isn't going to be affected by this, but it's got an argument of pi over 2. We just have to halve the argument, because you multiply the moduli and add the arguments when you're multiplying two complex numbers together. Well, when you're square rooting a complex number, you need to square root the moduli, but you just half the argument. So I can straight away just see that that's going to be 1 over root 2 plus 1 over root 2i. I hope you can see my sort of clever way of square rooting I there. It's kind of like in quite a casual way I'm doing it, yeah? Okay, so I then got root 2 times by 1 over root 2 plus 1 over root 2i. Yeah, and that gave me 1 plus I. Now, what have I just found here? I've found a root of this equation, yeah? And roots occur in conjugate pairs. So 1 minus I is a root as well, yeah? And it doesn't take too much thinking once you understand how these roots work. Ollie, what have you got there? Sorry, my son's just picking up things in my shed. He can be a tricky customer. But yeah, so it doesn't take too much thinking to realise the other pair of roots, because the roots occur always geometrically around here in a lovely even way, that one's going to be minus 1 plus minus 1 minus I and minus 1 plus I, yeah? So I've got all four roots, and now what I can do is, and this is what I genuinely did, I then thought, well, I've got the four roots, I'm going to find the sum and the product of those roots, so I can find, because I'm just trying to turn this into, I'm trying to factorise it, yeah? So I'm finding all the factors. So I realised then that n to the 4 plus 4 is equal to, right, okay, if I find the sum and product of the 1 plus I and 1 minus I here, well, the sum of it is clearly 2, and the sum is minus b over a, so that's n squared minus 2n, that's your minus b, because your a is 1, and then I multiplied them together and I got 2, because 1 plus I times 1 minus I is 2, yeah? And it's very similar for the other one, but you're going to get n squared plus 2n plus 2. And once I've factorised it, that's nowhere near as easy, is it, as the other one. But yeah, there we go. 1 second, I'm going to pause the video because I've got something. Okay, apologies for that. I just had to pause the video. You wouldn't have noticed. It's family emergency. But okay, so that was my stupid way of factorising n to the 4 plus 4. I kind of feel in this question now, if they just asked me to, like, or hinted that this could be factorised into 2 quadratic factors, I would have got to the answer much quicker. What they wanted you to do was to recognise that a substitution can be made, and I think the substitution was that root 2n equal m. Yeah. Now, both of those are real numbers, you know, or they're in a set of real numbers. And so what we can do is say, well, n is therefore m over root 2. And this isn't particularly complicated, is it? Actually working through the, cranking through the algebra. We're going to have m to the 4 over root 2 times root 2, which is 2, times root 2 times root 2, which is 2. So 2 times 2, which is 4, plus 1 equals. And then what are we going to have? Well, for n squared, we're going to have m squared over 2 plus m plus 1 and m squared over 2 minus m plus 1, and then you just times everything by 4 and you come up with the result. Yeah, so m to the 4 plus 4 equals m squared plus 2m plus 2, and what I've done is I've times that one by 2, and I'm going to times this one by the other 2, because 2 times 2 is 4. Okay, and we get that. I'll just quickly finish off my explanation. It's dead easy now. I didn't bother with any completing square like Mark Scheme did. I just thought, well, okay, if we want this to be prime, let's say we want this to be prime, because we're trying to deduce what you know, how many prime numbers n to the 4 plus 4 could be, yeah? Well, you know, forget n and just deal with m, yeah? You know, that's the thing, and I think that's what's confused you, the fact that we're now dealing with m, yeah? When could this be prime? This is prime if and only if the big number, and this is clearly bigger than this one because m's positive integer, yeah, if and only if m squared plus 2m plus 2 equals m to the 4 plus 4, whilst, or and if you like, m squared minus 2m plus 2 equals 1. Yeah, and I've then just solved this. This gives me m minus, because that's going to be m squared minus 2m plus 1, so that's m minus 1 squared equals 0. So m equals 1. At that point, really, I know it's either A or B, and like I said, I've already know it's not A, so it must be B, because there's only one value of m for which that holds true. Now, it really should work in this one. Now, to check it works, you could take it, turn it all into a quartic and factorise the quartic. That does work, but you could just plug in 1. 1 plus 2 is 5, and 1 to the power 4 plus 4 is 5, yeah? M equals 1 solves both, and it's the only number which solves both, because it's the only number which solves that, and therefore it's prime for only one positive whole number, n. Yeah, and that's what we can deduce. But it is a weird question, I agree. Like I say, I did it in a really silly way. But, you know, for those of you who've been in my class before, you know I love a ridiculous, stupid appeal to complex numbers to solve simple problems. You know, just for the fun of it. Okay, H I preferred. I thought it was quite a nice question in some ways. So what do we got? We've got 2x cubed plus 7x squared plus 2x plus 3 equals log base 2 of x plus 1 cubed plus, and 1, I'm going to turn that into log base 2 of 2. That's standard technique. Add it together, you're going to get log base 2 of 2 times x plus 1 cubed, yeah? Now, you might naively think at first, and actually you get away with it if you did, because it happens to be the case, you might naively think that all you've got to worry about is how many solutions there are to this cubic equals this cubic, yeah? Now that actually ends up being the case, but remember though, we can't log negative numbers, so you do have to bear that in mind and think about essentially the output, the range of this cubic, because you're going to plug it into a log function, and that has to be greater than 0. So we're only looking for solutions where this cubic equals this cubic, whilst both of them are greater than 0. So I thought sketching was important here. So I did a little sketch of this one. That's clearly just a cubic moved back 1. You know, y equals x cubed graph, I mean moved back 1, and it's going to go up something like that. Yeah, so that's y equals 2 open bracket x plus 1 all cubed. This one was more difficult to draw. I kind of figured, well, Um, hmm, you know, I looked at some values like -1, -2, -3. At -3, I started getting close to this being 0, so I figured the root was between -3 and -4. I checked whether it had any turning points as well, which you can do super quick, because you just got to differentiate it and check the discriminant. So I did do that. I got like 6x squared plus 14x plus 2, and after a quick calculation of that squared minus 4 times that, you get 196 minus 4 times 6 times by 4ac times 2. Okay, that does have turning points, yeah, and so that makes you think, well, it's probably going to do, I don't know, something like that. I don't know exactly where the roots are, but something like that, yeah. The way you can obviously check that there are two roots, and both of these roots from this diagram, suddenly, if I was doing this in a rush, I'd think, well, both of those occur after this graph is positive, because I know, like I say, just through inspection, basically a change of sign on this. If you plug in -4, I think you get a negative, whereas if you plug in -3, you're going to get a positive. So it's above the x-axis and below the x-axis. Now, to check that you do get two roots, you can just equate 2x cubed plus 7x squared, and it kind of annoyed me that you would have got away with this if that's all you checked, equals 2x plus 1 cubed, because in that sense, if you did it without thinking carefully, you could accidentally get the right answer, which kind of annoyed me a bit, because normally they have a sting in their tail, these questions, but especially as you get later on into the thing. But yeah, all I could see here was this was going to be 2x cubed, this is x cubed plus 3x squared plus 3x plus 1, so this will be 2x cubed plus 6x squared plus 6x plus 2, and I just quickly rearranged it into x squared minus 4x plus 1 equals 0. I did actually solve it, and I got x equals 2 plus or minus root 3. And I quickly thought root 3 is about 1.7. Both of them are positive. They're definitely greater than -1, which is probably, this one's a danger because you want to be greater than -1. And so there's two solutions there. Yeah. Okay, I quite liked. I like this. It just seemed to appeal to me. I didn't like reading it. I thought this sounds really hard. But then when I started to model it, I thought this looks absolutely lovely, actually. So what did I do? I just quickly thought, well, they're both tossing 5 fair coins, and they've both got exactly the same situation. They could get 0, 1, 2, 3, 4, or 5 heads. Yeah. Now Alice wins. I looked at P1. It probably would have been easier to look at P2 because all of the P2s are different, all of the P1s are different. So you've only really got to work out. Oh, apart from the last one. But if you don't get a third, then But yeah, so I only looked at like P1, but it probably would have been easier to look at P2. But this is what I did. I thought this is just a half to the 5. This is just 5 times a half to the 4 times a half, which is 5 times a half to the 5, yeah. So this is just classic binomial probabilities, this really is. This is 10 times a half to the 5. I'm just using, and in the old days this was common knowledge. Now you all use calculators. I suppose it's not so widely understood, which is such a shame, yeah. But this is just, all I'm doing here is using n choose r multiplied by p to the power of r multiplied by q to the power of n minus r, where q is 1 minus p. And this is a half to the power of 5, yeah? So these are the probabilities of tossing 0 heads, 1 head, 2 heads, 3 heads, 4 heads, or 5 heads. It's a binomial distribution, yeah? Now, if you want Alice to win, which is, of course, P1, then how are we going to work that out? Well, she can't win if she gets no heads, because the best you can hope for is a draw then by Bob getting no heads. But she could get 1 head and Bob gets no heads. So she needs 1 head, and Bob needs no heads, yeah? Or she could get 2 heads, so we'll do that. And remember, Bob's got the same binomial distribution, and Bob could get 1 or no heads. Now, this is really a 1 time, so we can just add those two together to find the probability of getting Bob getting 1 head or no heads. So I'm going to times that by 6 times a half to the power of 5, yeah? And then, very similar, 3, it didn't take too long, multiplied by her getting 2 or less, so 10 plus 5 plus 1, 16 times a half to the power of 5. Plus 5 times a half to the power of 5. I'm going to run out of space. Running out of road here. Let's put that there. Okay, times, and then, 3 or 2 or 1 or 0. So that's 26 times by a half to the power of 5. Hopefully I can see that 26 and my handwriting doesn't spoil it for me. Or she gets all 5 and Bob gets 4. Well, that's 5 plus 10 plus 10 plus 5 plus 1. So that's 31. Times by a half to the power of 5. Yeah, and I thought if this works I'm going to be really pleased. Well, sure enough it did, because those are all half to the power of 10s. And then you've got 5 plus 10 plus, sorry, 5 plus 60, that's 65. And then you've got 160. And then you got, like, what is that? 5 times 26, well, that's 130. And then 31. Yeah, and I just got to add up all of those. So I've got a half to the power of 10 times by, what is that? 290, 290, 321 plus 65. I think that's going to come to 386. Yeah, a half to the power of 10, that's a power of 10. My God, that handwriting is terrible. Times by 386, and I realised that that's the same as 386 over 2 to the 10, which is the same as 193 over 2 to the 9. I'm pretty sure that's 512, isn't it, from memory? And so I figured it must be A, because that's the only one with P1 equals 193 over 512. Afterwards I thought, why didn't I do the draws, because there'll be less to consider. They've either both got to get 0 heads, or 1 head, or 2 heads, or 3 heads both, or 4 heads both, or 5 heads both. That probably would have been easier, thinking about it. But there we go, that's what I did. I wanted to show you not what the easiest way is necessarily, because good stuff if you saw the easy way, but I do like to show you realistically, like, what crazy stupid things all of us do sometimes. Now here's a good example. J is a funny one on these papers. I either find it really nice or really exceptionally nasty, and this is one of those ones where if you don't try and do this algebraically, it's really nice. And this is exactly the approach they've got in the mark, in the mark scheme. This first one, it should be fairly clear that y equals mx plus c. You've made a substitution here for y for mx plus c. So this is like, there's a circle, x squared plus y squared equals 1, yeah? And a straight line, if which is touching it if it's got a repeated root. Well, a straight line is y equals mx plus c. And then we've got another circle, 3 across and 1 up, yeah, also radius 1. So it looks something like that, yeah. And they're basically saying, and this one's got a repeated root with the same straight line, because this is still y equals mx plus c. So they've both got to have repeated roots, i.e. the line is tangential to the circle. And they're basically asking how many possibilities are there for the line. Well, graphically speaking, it's really easy, because you can just go, there's that possibility, or of course, there's that possibility. Okay, so those are the two possibilities for it being tangential over there. Or you can have, and remember they're both radius 1, this possibility, so that should be actually parallel to that one, or there could be this possibility. Yeah, notice that the roots aren't necessarily in the same place, and those are the only possibilities. So the answer's 4. That's clever. That is. That's a really clever one. It's one of those ones as well. You either spot it or you don't. I did start doing the algebra, by the way, on that one, and then I thought, hang on, I'm dealing with two circles. Is there a better way? So yeah, never hurts to suddenly ponder and think, is there a better way? But yeah, last 5 questions are tougher than the first 5 always. Try and spend, I know you get an hour on these tests, these 10 questions. My advice, for what it's worth, is 20 minutes on the first 5, 40 on the second 5. But I mean, that's arbitrary. It really is. And you want to get as many out of the 40 marks available for the first 10 questions as you can, because if you can hit 32 or 36 out of 40 there, you're doing really, really well. You really are. And then you just need, and don't get me wrong, the longer questions I think are harder, but you just need a good performance on 2 or 3 longer questions, and you're looking good. You're suddenly looking very strong. Okay, so I hope that was useful. Carry on the good work. And all the best. Bye bye.